Hi, I'm Zor. Welcome to Unizor Education. Today's lecture is double sequences and their limits. Double limit of sequences. Now, what is double sequence? Well, usually a sequence is something which depends on one index, like x, n, where n is natural number, 1, 2, 3, 4, 5, and x is some usually real number. Okay. Now, today we will talk about double sequences which depend on two indices. Well, obviously, in the future, if it's necessary, we can go into any number of indices. But in this case, and I think it's completely sufficiently, we have two indices, a and m. Well, if the regular sequence can be imagined as a function of 1, 2, 3. So this is x1, this is x2, etc. Now, if we are talking about double sequences, we need three-dimensional space, right? So we will have some kind of a matrix 1, 2, 3, 1, 2, 3, and on the crossing of any two indices, we will have some kind of value, for example, 25.5. Graphically, it will be represented as, let's say, some kind of a column in the three-dimensional world. So this is the representation of double sequence. Okay. Now, we're talking about limits. So this is a trick now. Now, again, if there is no problem defining the limit of function of one index, so if this thing converges to some kind of x, it means that the difference between them is less and less and less, and using the more scientific language, for any neighborhood of the size of epsilon, we can find some number n such that if index is greater than n, then the difference between the limit and the sequence would be less than epsilon for any kind of n greater than n capital. Okay, so that's the regular limit. Now we're talking about double limit. So double limit question is which index we are using, the first one or the second one or both of them, etc. And that's basically the subject of today's lecture. Okay, now this lecture is part of the course called Math4Teens, and it's presented on Unizor.com. I do suggest you to watch the lecture from the website, from Unizor.com. It is totally free and there are no advertisements, etc., as you can find somewhere else, like on YouTube, for example. You don't even have to sign in if you don't want to. It's just formality. Now, what's important is that the website contains courses, like Math4Teens is a course. There is a Math Plus for all, basically. That's another course. There is a course Physics Plus. So you have certain number of lectures presented in certain sequence, divided in certain like chapters or parts, and you have menus which you can choose basically which route to choose. Plus, every lecture has textual supplement, which is basically like a textbook, explaining the same thing which I'm doing during the lecture, but maybe slightly differently, maybe in somewhere I missed something during the lecture, but I compensated in the write-up. So I do suggest you to, after or before you watch the lecture and the video, I do suggest you to read the corresponding text on Unizor.com. Okay. So let's go back to our problem. Let's give you an example, pure artificial example. So let's talk about the following. Arctangent of m plus 2 minus n. Okay, so we have to know how this particular double sequence behaves when both indices go to infinity? Well, it means that in this table we go to infinity by both arguments, by both indices. We can go, for example, here to infinity and then here to infinity. So it will be the vertical column and then the horizontal. Or it can be vice versa. It can be on each horizontal count I will get to some kind of a limit. This would, let's say this would be B1, B2, B3, the limits of those things. If I go down all the way to infinity, I will get, and these are some numbers. So these numbers are converging to B1. These numbers are converging to B2, etc. Then I can go to infinity among the limits and get some kind of a number. Okay, alternatively, I can go horizontally. So I can go to this particular row and get some kind of a number C1 as a limit of these numbers to infinity, C2, C3, etc. So for every row I can get some kind of a limit. And then I can see where are these limits are going. And they might actually go to the same number or might not, because we are doing completely different things. Well, let's use this particular example. If I'm fixing m and going by n, it will go to, well, if I go by n, it will be obviously to 0. So it will be only arctangent of m remaining. Then if I will go to infinity by m, well, if you remember, the graph of arctangents is something like this. This is p over 2, this is minus pi over 2. So the limit would be pi over 2. Let's do it differently. First we go to infinity by m. So arctangents by m would be pi over 2 plus 2 to the minus n. Now I will go to infinity by n. This will go to 0, so again I will have pi over 2. Same thing as here. Alright, great. At the end of this lecture, I will give an example of a different kind of behavior. But right now, let's concentrate that probably in most of the cases, that would be the case, in which case we can talk about the limit of double sequence, because no matter how we do this limit, we still go to the same number. If we go to different numbers, it means this particular double sequence doesn't have a limit. All right. So now let me go to a more mathematical presentation of this. So we will prove some theorem which basically gives you sufficient conditions for double sequence to have the real limit, no matter how you calculate it. Okay. So first, before doing this, I would like to present a new concept. It's called uniform convergence. Well, you don't need this for a sequence of one index, but if you have a double index, you do need something more than just convergence. You need uniform convergence. And here is what it means. In case of our table, for example, remember we were using this table? So these are A11, A12, A13, etc. This is A21, A22, A23, etc. A31, A32, A33, etc. Now, let's consider we are going vertically, and we get B1, B2, B3 as limits. Okay, so in a very non-scientific way, uniform convergence means, well, obviously not only that each column converges to some number, but also, at least starting from certain number, they're all converging at the same way. So the difference between the limit and the concrete value of the double sequence will get smaller and smaller for all of these at the same time. Now, I would like not to consider the cases when this thing is this column is converging to this limit with one speed, and this column and this column would converge to their corresponding limits with different speed. I need speed to be the same, which means I would have, for every neighborhood epsilon, positive epsilon, I will have some number n such that not only a m n would be close to some kind of a limit bm. So this is bm, this is am1, am2, amn. Not only this would be less than epsilon for any n greater than n, but also for any m as well. That's what's important. So not only each row contains the sequence, if m is fixed, contains the index by n when the corresponding element of the sequence is close to this one after certain n. But also after certain n, all these would be also as close to this to their corresponding limits. So the elements of the double sequence will be close to their corresponding limit, closer than whatever epsilon I choose. Not only if I'm going sufficiently down, greater than n, vertically in the sequence itself, but also in another index as well. That's what uniform basically means. That's very important, and that would be very important part of the proof of the theorem, which I'm going to prove right now. Okay, so we know what uniform convergence is. All I need is, if my n is changing and m is fixed, then amn will be close to corresponding bm, m is fixed, n is changing, m is fixed. After a certain number n, not only for all n greater than capital N, but also for m as well. All right, so we know that. We know what uniform convergence is. It's a stronger convergence than convergence by each index separately. Because obviously we can talk about each index separately. We fix m in am and change only n, and then it will go to bm. Or we can fix n. This is fixed, fixed m. Or we can fix n, and amn would be going to some kind of c fix n, as m goes to infinity, n goes to infinity. So sufficient, is this sufficient? No. The question, the answer to this question is no. Separate convergence is not sufficient condition for the amn to be to have a limit, no matter how we change m and n. But if it's a uniform conversion, then yes. All right, so here is the theorem which I have. For instance, we have a separate limits for m and n. And also we have that if after we change, we calculate the limit for each m, then I will go to some kind of a b if m goes to infinity. So there is another limit of the limit. So this is basically limit a m n. First we do n goes to infinity, then we go m goes to infinity. That's what this is. Bm is limit of a m n if n is changing, and then I'm going to infinity by m, and that goes another thing. Similarly, I assume that Cn also have kind of a limit if n goes to infinity. So this is what? This is limit of a m n. But first we do by m, and then we do by n. The theorem is, if this is true, and this one are uniform convergence, not just convergence, but uniform convergence, then these two limits are equal to each other. That's the theorem. So again, if I have limit by one index, and then limit of limits, but this one is uniform, or I change the sequence. If I go to the limit by another index, and it's also a uniform convergence, and then I do limit of limits, then I will get exactly the same result. And then we can talk about basically limit of sequence, that as it will be an existing b is supposed to be equal to c. Now, the proof is actually very simple. I spoke for a length, but it's really a very simple proof. Here it is. Okay, let's just wipe out this. Okay, here it is. Let's do this. Assuming b not equal to c, and b minus c is equal by absolute value, let's say d. I will come to obviously some kind of contradiction if I assume this. All right, so now if this is true, then let's take epsilon is equal to d over 4. You'll see why just a little later. Now for this particular epsilon, and this is a limit, bm is a limit of amn as n goes to infinity, then there exists such number n that difference between amn and bm is less than my epsilon, which is d over 4. When n greater than n, and because of the uniformity of the conversions, m also is n. So for any m and any n greater than this number, let's call it n1, my inequality is true. For sufficiently big m and n, this is what it means, sufficiently big. This is true. Okay, great. Now, at the same time, I know that bm goes to infinity, to capital B, which means for the same, let's say, epsilon equal to d4, I will find another number m, let's call it m1, such that bm minus b less than d4, right? If m is greater than n1. This is n1. Okay. Let's choose m1 greater than n1. I mean, we can, since it's for every m, lowercase m greater than m1. If m1 happens to be less than n1, then we will upgrade it to n1. So we are assuming that this is greater or equal to n1. It will be even better in this particular case, right? So if m1 is less than n1, we will, instead of m1, we will put n1. So whatever the number is, let's call it m1. Both this and this is true. But now let's think about the difference between bm and b is less than d4. So if this is d4, this is b. This is b minus d4 and b plus d4. So somewhere there is bm. And difference between mn and bm is also less than d4. Okay, in the worst case, it would be d4 and d4. So the difference between b and amn is definitely less than sum of these two differences, right? What does it mean? Well, it means that the difference between amn and b is less than d4 plus d4, which is d2. So amn is no further than d2, d over 2 from b. Okay, now I will prove exactly similarly that amn is closer to c than d over 2. And here it is. Again, it's absolutely the same. Well, I can say it's just analogously, but I would like to repeat it again so you will just have this logic a little bit better. Okay. So we go by a different index. We have amn goes to cn if m goes to infinity. So by second index is changing, first index is changing, the second index is fixed. In turn, cn goes to some kind of a c if n goes to infinity. I assume that this is a uniform convergence, which means what? That for any epsilon, which I will took exactly the same d over 4, my difference between amn minus cn would be less than d4 if m goes to infinity, right? So m is supposed to be greater than some kind of n, m2. But since it's a uniform conversion, that would be n as well. Now, on the other hand, I know about this, which means that for the same epsilon equals to d4, difference between c and cn would be less than d over 4 if n greater than n2. And now, again, the same trick. If n2 is smaller than m2, we will take m2. So that would be even better. So whatever n2, we will choose at least the maximum between the old n2 and the new n2, and old m2. So in any case, if this is true, both this is true and this is true. So amn from cn no further than d4, cn from c no further than d4, which means that amn minus c is d4 plus d over 4, so it's d over 2. So what do we have right now? We have this and we have this. Now this is, if you remember, if mn greater than N1, I don't remember, it was M or N, doesn't really matter. Yeah, N1, M1. And this one is if M and N greater than N2. So if I will get maximum between M1 and N2, both will be true. Okay, so for some large, sufficiently big M and N, both, so after both of them are over a certain number, which is maximum of these two, both are true, which is impossible because if B and C are on a distance d, you cannot have number A and N which is closer to this one less than d2 and closer to this one less than d2. Then the difference cannot be d, obviously, right? Because even if it's here, right in the middle, it will be equal to d over 2. So if this is less and this is less, there is no basically way to put A mn closer than d over 2 for both for both B and C. Which means what? Which means that B is equal to C, which is supposed to be proven. Well, that's it. So this is a sufficient condition for the sequence, double sequence, to have limit when both indices are going to infinity, and doesn't really matter you go by one index to a limit which will be a function of another index. In this case, for example, we go with m to infinity, then it will be a function of n, and then we will go limit of limit by second index and get some number, or you do in the right vice versa. You first go n to infinity, and that will be a function of m, like bm, whatever, and then go to infinity by the second index. And again, if this is true, if this is a uniform conversion in both cases, you will have the same result. Okay, and I promised to give you an example. The situation is not so simple. And it's really very simple example. Okay, consider sequence. A m n is equal to m over n. What happens? Well, if m is fixed and n goes to infinity, what do we have? Well, obviously the limit will be 0, right? So it goes to 0. Now, what happens if n is fixed and m goes to infinity? Well, there is no limit. It will be 1 over n, 2 over n, etc., 3 over n, 2500 over n. So if n is fixed, we will have a sequence which has no limit. I mean, sometimes you can say limit is infinity, but that's not limit. There is no such thing as infinity as a number, right? So there is no limit. So that's a contradiction, obviously. So, but that's a sequence which really does not have a limit when m and n goes to infinity. That's basically a simple example. As simple as it can be. Okay, so basically that's it. Again, my purpose was to, well, two purposes. One purpose was to introduce a concept of uniform convergence. So that's very important. It will be very important for limits of functions as well. We will do another lecture. And obviously some sufficient conditions for a double sequence to have a limit. Now again, I suggest you again go to unizor.com, go to Math4Teens course, Calculus, and then you will have limits of sequence, series of lectures, and one of the lectures is called double limit sequences. That's it for today. Thank you very much, and good luck.